Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this deep dive into Apache Sedona, the open-source powerhouse for scalable geospatial analytics. Sedona brings spatial intelligence to big data by integrating seamlessly with Apache Spark. Whether you're analyzing millions of GPS points or modeling spatial trends, Sedona delivers high performance and flexibility. In this tutorial, we'll explore its architecture, core features, and real-world applications. Geospatial analytics is transforming industries by enabling data-driven location insights. From optimizing delivery routes to modeling urban growth, spatial data is crucial. But processing massive geospatial datasets is complex and resource-intensive. Apache Sedona solves this by leveraging Apache Spark's distributed computing power to scale spatial operations efficiently. Apache Sedona introduces native spatial data types like point, polygon, and line string into Spark. It also supports spatial indexes such as R-Tree and QuadTree to accelerate queries. With spatial SQL support, you can run complex spatial joins and predicates using familiar SQL syntax. These features make Sedona both powerful and accessible. Sedona's architecture is tightly integrated with Apache Spark. It extends Spark with spatial RDDs and data frame APIs. The spatial SQL engine allows you to run spatial queries with predicate pushdown for performance. Indexing support like R-Tree and QuadTree enables efficient spatial joins and range queries. Sedona supports standard OGC spatial data types. A point represents a single location like a GPS coordinate. A line string connects multiple points, useful for roads or rivers. Polygons define enclosed areas like countries or lakes. Geometry collections allow you to mix different geometry types in one structure. Efficient spatial indexing is critical for performance. Sedona supports R-Tree, which excels at range queries, and QuadTree, which is great for partitioning space. These indexes dramatically reduce query times by pruning irrelevant data. Sedona handles index creation and usage transparently under the hood. Sedona extends Spark SQL with a rich set of spatial functions. Functions like stcontains, stintersects, and stdistance let you express complex spatial relationships. Predicate pushdown ensures these operations run efficiently. You can even perform spatial joins using familiar SQL syntax, making it easy for analysts to adopt. To get the most out of Sedona, optimize your workflows. Spatial indexes are key for large data sets. Partitioning your data spatially improves parallelism. Predicate pushdown reduces data shuffling. And caching frequently used datasets in memory can speed up iterative queries significantly. Let's look at a real-world use case: urban planning. City planners can use Sedona to analyze GPS traces and traffic density. They can identify underserved areas and model the impact of new infrastructure. Results can be visualized using GIS tools to guide policy decisions. Getting started with Sedona is straightforward. First, install Apache Spark. Then, add Sedona's Maven dependencies to your project. Configure spatial serialization for efficient data transfer. Finally, register Sedona's spatial functions with Spark SQL to enable spatial queries. Sedona supports various spatial data formats like CSV, GeoJSON, and shapefiles. You can load data using Sedona SQL or Spark's built-in readers. Once loaded, convert it to a spatial data frame and apply spatial indexes for performance. This prepares your data for advanced spatial analytics. Once your data is loaded, you can run powerful spatial queries. Use stIntersects to detect overlaps, stdistance for proximity analysis, and stbuffer to define zones of influence. You can also perform spatial joins using the data frame API for more complex workflows. Spatial joins can be expensive. To optimize, use spatial partitioning to align data distribution. Enable spatial indexing to prune irrelevant pairs. Avoid full Cartesian products by filtering early. And cache intermediate results to speed up iterative workflows. Once you've processed your data, visualizing results brings insights to life. Export to GIS tools like QGIS for detailed mapping. Use Kepler, PostGL for interactive web visualizations. Generate GeoJSON for dashboards or integrate with BI tools for reporting. How does Sedona compare to PostGIS? PostGIS is SQL only and runs on a single node, making it ideal for traditional GIS workflows. Sedona, built on Spark, is designed for distributed processing and scales with big data. Both support OGC standards, but Sedona excels in distributed environments. Apache Sedona shines when you need to process massive spatial datasets. If you're already in the Spark ecosystem, Sedona integrates seamlessly. It's ideal for real-time or batch workflows that require distributed processing. However, for small datasets, simpler tools might suffice. While Sedona is powerful, it has limitations. It assumes familiarity with Spark, which can be a barrier. It lacks native visualization, requiring external tools. Spatial concepts can be complex for newcomers, and while it supports core spatial operations, it may lack some GIS-specific features found in dedicated tools. Sedona has a vibrant open-source community. Check out the GitHub repo, mailing lists, and official documentation. There are plenty of tutorials and examples to get started. The community is active and always welcoming new contributors. For advanced users, spatial partitioning is key. Grid-based methods divide space into tiles. Hilbert curves preserve locality, reducing shuffling. These techniques improve spatial join performance and overall query efficiency in distributed environments. Sedona offers a rich set of spatial functions. SDBuffer creates zones of influence. SDCentroid finds geometric centers. SDConvexHull computes enclosing shapes. SDUnion merges geometries. SDSimplify reduces complexity. And you can write custom UDFs for domain-specific logic. Let's look at some performance metrics. Query time increases with dataset size, but spatial indexes help. Partitioning reduces join costs, and caching in memory trades space for speed. These metrics guide optimization decisions in real-world deployments. Security is critical in geospatial analytics. Encrypt data in transit and at rest. Use Spark's ACLs for access control. Secure communication with Kerberos, and maintain audit logs for compliance. Sedona inherits Spark's security model, making it enterprise-ready. In retail analytics, Sedona helps analyze foot traffic, identify store locations, and predict demand using spatial clustering. You can visualize catchment areas to understand customer reach. These insights drive strategic decisions and improve ROI. Looking ahead, Sedona is evolving. Planned features include better visualization support, native Flink integration, enhanced ML pipelines, and improved GIS interoperability. These updates will make Sedona even more powerful for spatial data science. To recap, Sedona brings spatial data types, indexing, and SQL support to Spark. It offers both SQL and RDD APIs for flexibility. Performance optimization techniques like indexing and partitioning are essential for large-scale analytics. Ready to get started? Install Spark and Sedona. Load some sample spatial data. Run your first spatial query, and explore performance tuning options like indexing and partitioning. These steps will set you on the path to mastering Sedona. Apache Sedona is a game changer for scalable geospatial analytics. With tight Spark integration, rich spatial functions, and strong performance, it's ideal for big data workflows. Its growing community and expanding use cases make it a tool worth mastering. Thanks for watching this deep dive into Apache Sedona. If you found it helpful, hit like and subscribe for more big data tutorials. Let me know in the comments how you're using Sedona or what topics you'd like to see next. Sharing is caring. Spread the knowledge. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.